John ZuHone. I'm at NASA Goddard. Developed using Python as well as YT, AstroPy, and some other packages, an analysis module and a pipeline to simulate X-ray observations with the help of these collaborators that you can see here. So X-ray astronomy probes the high-energy universe, and primarily when I think about the things that X-ray astronomy is probing, I think about high-temperature plasmas like in galaxy clusters or the solar corona, or relativistic cosmic rays such as inverse Compton scattering off of the CMB in galaxy clusters, or what's produced in active galactic nuclei, or a number of other processes. So we have these excellent observatories. These aren't all of them here. These are just some of the ones I want to highlight, which have either been launched up into orbit already, or in the red, the ones that are coming up. In the next year, we'll have Astro-H launched by Japan, and European Space Agency will be launching Athena. And this is going to be sort of a new era of X-ray astronomy where we're going to be able to actually measure very precisely the width and shift of spectral lines to tell us about the motions of gases in clusters and other objects. So as I've already mentioned, X-ray astronomy looks at a lot of different interesting different objects. The galaxies, the gas in galaxies gives off X-rays. Supernova remnants produce X-rays. Galaxy clusters produce X-rays, and also there are X-rays produced at the very centers of galaxies by AGN. One thing that's really important to note about X-ray astronomy, and of course, even though I'm not talking about it today, it's also true for gamma ray astronomy and maybe hard UV astronomy, is that we're dealing with small number statistics. The continuum approximation, where you can basically say, okay, I have an image where the flux of photons from my source is basically completely flooded my image, and I can just say I have an intensity of emission in each pixel, is not exactly valid. So, I mean, you can make images of X-rays, but fundamentally the data products of X-ray astronomy are actually tables of photon positions, photon energies, and arrival times. And so we're definitely dealing with small number statistics, both as you can see for the image, and also as you can see from the spectra, particularly down at the high energy end, where the number of photons in a particular energy channel gets very, very small. So if we want to simulate these kinds of observations, we can't just make flux maps. We actually have to simulate the photons themselves. Now, why would we want to simulate X-ray observations or any observations in the first place? Well, theorists like me are building simulations, and simulations, at least the best ones, are 3D, right? Or maybe some approximation of 2D, like a 2D cylindrical or 2D spherical situation, but observations of astronomical objects are 2D projections on the sky, right? So we've lost one dimension there. You're collapsing, that radial dimension, if you will, all along one axis. Simulations, like hydrodynamical simulations or in-body simulations, consist of physical quantities like density, temperature, velocity, composition, metallicity. But observations are collections of photons which are emitted from physical processes that are fundamentally dependent on these quantities, right? So there's a couple of jumps in terms of, like, you have to model the system properly, and then you have to model the emission properly to actually get you to the observation. And the other thing is that, at least we hope, simulations generally only model what you put into them, modulo, sources of numerical error. But observations include lots of contaminating backgrounds and instrumental effects. So it's important, in order to be able to, compare our simulations to observations and see if we're actually modeling actual astronomical objects correctly, to produce observations that can make predictions for what observers might see or explain what observers have already seen. So one such package that does this for X-rays is PhoX. It was written by Veronica Biffy. There's a paper on AppJ, and there's also a website where you can actually download the package. The original PhoX package is written in C, and it's only designed for gadget data. So it has great utility, but it's limited to that particular space. So PhoX is kind of a novel kind of algorithm when it comes to simulating X-ray observations. Most previous attempts at simulating X-ray observations, what started with this is that you pick a projection of your 3D simulation, you make a flux map of that projection along the line of sight, and then you use that flux image along different energy bands as a map to generate photon samples. Now it works just fine, but the point is that this is actually a very expensive procedure often, especially if you have a high resolution simulation and you want a high resolution image and you want lots of spectral resolution. So the instant that you have to make many different lines of sight, or maybe want to simulate, different aspects, anytime you want to do lots of different observations, this can become a very expensive procedure. So Veronica's approach in PhoX was to instead essentially discretize the emissivity in 3D first. So generate a large sample of photons in the 3D space in the rest frame of the system, which is still the most expensive step, but only do that once. And then you use that large sample of photons every time you want to make a particular observation along a particular line of sight or with a particular instrumental model. You draw subsamples from that large sample, and then you make projections along any line of sight you want. So the most expensive step for a given system only has to be done once, and then the less expensive steps you can repeat as many times as you wish. So we've taken the PhoX algorithm and we've implemented it in the simulation analysis package and visualization package YT, which is going to be talked about later this afternoon. And there are some advantages to that, which I'll describe in the next slide. But the basic idea is that you have a 3D numerical simulation, such as a slice of the density of this one from a Athena simulation. YT is able to get at the data. YT has a version of PhoX that basically generates the photons, and at the end you can produce a synthetic observation. So why do we use YT? Well, I'm only going to give a few brief bullet points on this. For the first reason that we have a really good website, but more importantly, if you really want to know, you should come to Nathan Goldbaum's talk at 3:50 in this room, I believe. So if you really want to hear the scoop on what's going on with YT, especially all the new features in version 3.0, not only for simulation data, but also observational data and a lot of other aspects, you should definitely come to that talk. So I don't want to steal his thunder, but I'll just illustrate a couple of bullet points that are going to be useful for why we implemented our X-ray analysis module in YT. The first is that it reads simulation data from a variety of different simulation codes. Flash, INZO, Gadget. You can even read generic NumPy array data if it's in a sensible format. So you're not restricted to just one type of simulation data. The second is that it provides windows onto the data that make sense from a physical perspective, not just a computational perspective. So what I mean is, and Nathan will describe this in more detail, is that instead of thinking about the computational components of the simulation or the data set, like the cells, the particles, the way things are laid out on disk, you actually think about physical volumetric optics like spheres, disks, or you actually think about the physical fields as they are distributed in space, like density and temperature. And the other nice thing about using YT is that we can make use of this broad scientific Python ecosystem for not just science, but also astronomy. So we can make use of things like SciPy, AstroPy, ApplePy for plotting, etc. So what I'm going to do in the remainder of the talk is I'm just going to breeze through a quick example of how we can create a synthetic observation from a particular data set. So the example code I'm going to show is in the proceedings. It's also available as an IPython notebook that actually there's a link in the proceedings, so you don't even have to write down the link right now if you want. The code is implemented, at least in this example, in YT 3.0 beta, though it is also part of the current stable version, which is 2.6. So the syntax will be a little different in some places, but essentially it's the same procedure. And the path to the analysis module is yt.analysismodules.photon simulator. So just a few preliminary cells. Basically, we import the things that we need from YT, and then what we're doing here is that we're just loading up a data set. This is a Athena code data set, the Athena ImageD code written by Jim Stone. This is an Athena data set of a galaxy cluster core. And so what we're doing in this cell here is that we're just loading the data set, and then we're extracting a sphere centered on the cluster center that's 250 kiloparsecs in radius. So that sphere will give us the information about the density, temperature, velocity, and other aspects of that part of the cluster. So we can take a slice of this data set. On the left is density, on the right is temperature. This galaxy cluster core is undergoing what we call gas sloshing, so you have these spiral-shaped contact discontinuities that are cold on the denser side, and you can actually see these spiral-shaped discontinuities in X-ray surface brightness. So step one, we have to generate this big photon sample in 3D. So the first thing we need is we need a model. So imagine we have some extended object with density, temperature, velocity, metallicity as a function of position, like a galaxy cluster. So spectral models define an emissivity in photons per second, per centimeter cubed, per, say, some energy, in this case, kiloelectron volts. So you can imagine in terms of your simulation, you have all these cells, or you have all these SPH particles that have these quantities of density, temperature, and metallicity, and they're emitting photons at a rate that is determined by those given some kind of spectral model. So if we imagine just a cartoonish picture like this of a roughly spherical object, we have our little volume element here, a little cube. It's got a density, temperature, and metallicity, and it's sitting out there, and you can associate an emissivity with it, and you can draw photon samples from that. We'll come back to this figure in just a minute. So in order to determine what the flux of photons is and how much of that at each energy, we need a spectral model. And here's just an example of an APEX spectral model. So this is energy versus normalized counts per second, per centimeter cubed, per kiloelectron volt. And as you can see here, you have a continuum spectrum with a lot of lines on it. This is a fairly typical kind of spectrum for what you might see in a galaxy cluster. This is a 5 kiloelectron volt temperature and a metallicity of 0.3 solar. So we have, in the photon simulator, we have methods for basically defining models. This is a cell that basically chooses this particular APEC model as the startup model, and it also sets up a model for the photons that is a thermal model, because that's what the plasma in a galaxy cluster is a thermal plasma. And so we're telling it, you know, what the mass fraction of hydrogen is and what the metallicity is. This can also be spatially dependent, but in this case we're just having a constant metallicity. So I said we needed to generate a large number of photons because we're going to use them as a Monte Carlo sample to draw from. So how many? So what we probably want to do is that we probably want to generate a number of photons that is large compared with what we might expect in a typical observation. We want something that's statistically representative. So, you know, for a given observation, you know, the number of photons is going to be determined by how far away the source is, the collecting area of the instrument, and the exposure time of the instrument. So what we'll do is that we'll initially take values for these parameters, make them very, very different from what we might expect for real observation. So give like a ridiculously long exposure time, a very, you know, large collecting area, and maybe put the source at a fairly close distance. And then we can define a flux of photons, and then a number of photons based on that flux that is, you know, going to be at least maybe an order of magnitude or two larger than the amount of photons we might actually get in the real observation. So this way, you know, if we choose those numbers carefully, if we know what exposure time we're going to want, and we know what kind of instrument we're going to use, we can actually ensure in a very straightforward way to generate a large sample of photons in 3 dimensions. So this is just the Python code to do that. It's fairly straightforward. We have a class called Photon List that basically generates photons in 3D from scratch, given our original sphere object SP, values for the redshift, and these are, again, are the inflated values. We give it the thermal model that we specified earlier. We can also give it a cosmology. We can specify different cosmological parameters if we want, and we can write these photons to disks. So if we want to actually use them over and over again to produce many different realizations of 2D observations, we don't have to generate this object all over again. We can just read it back from disk. So that leads us to step 2, projecting the photons to create the actual observations. So this takes us back to this figure. Now, this little volume element here, represented by the cube, is traveling with a velocity vi in some direction. And we have some direction along the line of sight, straight up towards the Chandra telescope over there. And the photons are going to be Doppler shifted along that line of sight by the component of the velocity along the line of sight, which is that dashed arrow Vz prime right there. So we need to choose a line of sight vector along which we will project to produce an image. And then this line of sight vector is going to determine, based on the velocity of that volume element, how the photon is going to be either redshifted or blue shifted, depending on if the gas is moving towards or away from us. And of course, the photons are, if the distance to the object is cosmological, the photons are also going to be redshifted by the cosmological expansion. So we have to take that into account as well. Some photons, particularly on the low energy end, the soft X-ray photons, get absorbed by foreground galactic gas. So we have a way of using pretty commonly used models for the absorption cross-section to take that into account. And then we have to determine how many photons actually get observed, and this is where we take advantage of the fact that we choose more realistic values for the telescope collecting area, for the exposure time. We maybe change the distance to the source, and so we only get a fraction f of the photons that are actually observed. So we choose more realistic values for these parameters. And that, we can wrap all that up into a call that basically projects our original photons object and creates an events object, which is now a 2D, Doppler shifted, red shifted representation of an image that you might see on the sky. But there is one thing left, and it is, if we want to have a realistic representation of an observation, we have to take into account instrumental effects. So obviously, real astronomical instruments have a number of effects that alter the distribution of photons that is actually observed. So for example, and I'm thinking primarily in terms of X-ray telescopes here, we often think of it in terms of an effective area where the actual effective area of the instrument is energy dependent. And so this is something that you need to take into account, because the photons have different energies, that there's a different effective area for each energy depending on which one it is. And that the photon energies are mapped to CCD channels often in a non-trivial way, and this is encapsulated in a redistribution matrix. And what we do is that we provide a simple way to convolve photons with these responses. And so if you have an ARF or an RMF, again, this is more like X-ray parlance, then you can actually use a modified call to that project photons to actually convolve the photon distributions with those instrument responses. But sometimes you need a more fuller simulation of a particular instrument. And so for this, we provide output formats to export to existing software packages for simulating X-ray instruments. And there's just a couple of examples right here to simulators where we can output to certain file formats, where you can output to MARCS, which is a Chandra simulator, or other simulators like SimX and 60, which simulate a variety of instruments like XMM Newton, Astro H, even like Athena, which isn't even launched yet, but we still have the models for what these telescopes are probably going to be able to do. So to close up with some images, so here's a counts image of the galaxy cluster core that we saw in the beginning. So you can see, you can roughly trace out the spiral shape. If we had a longer exposure, it might be a bit more obvious. And here's an example of the spectrum, which has like a continuum in lines like the model, but of course it's been modified by the fact that on the low end you're absorbing some of the photons by the foreground intergalactic gas, and the photon distribution has also been convolved with that effective area curve I mentioned a minute ago. And we can use those instrument simulators to simulate the same object with the same exposure time for different instruments. So this is 5 different instruments. observing the same galaxy cluster. Everything has been rescaled so it's on the same scale. So this is Chandra, XMM Newton, New Star, Astro H, and Athena. And you don't have to have data set from a simulation. You can have in-memory data sets. So here's an example where I just took a galaxy cluster and evacuated a couple of bubbles. This was all done with NumPy arrays and did something similar. And so I think this is a really good start on a package, and this is my summary. And if there's any time, which it doesn't look like there is, we'll take some questions.
Okay, thank you.
Feel free to ask John.